Welcome back to my YouTube channel. So in this video, we'll be talking about heap trees. So what is a heap tree? A heap tree is a special kind of binary tree which we can use to quickly find and remove the smallest or the largest element. A heap tree must satisfy two properties. First one is the shape property and the other one is the heap property. So let's look at the shape property. What is meant by the shape property? Shape property means that a heap tree must be of the complete binary tree structure. So now what is a complete binary tree? So first of all, let's look at the binary tree. Binary tree means that each node in the tree can contain 0, 1 or 2 child nodes. That means each node can have at most 2 child nodes. One is left child node and the other one is the right child node. So a complete binary tree means that every level, possibly except the last level, is completely filled. And it's filled from left to right. And all nodes in the last level is far as left as possible. So by shape property, we mean that a heap tree must be of the complete binary data tree structure. So the other property a heap tree must satisfy is the heap property. There are two types of heap properties. First one is the max heap property. Max heap property. And the other one is the min heap property. So max heap property means that the value of each node must be greater than or equal to its children. That means the parent must be always greater than or equal to its children. So the maximum value is always at the root. So for an example, this can be taken as a max heap. So min heap property means that the value of each node must be less than or equal to children. That means parent is always less than or equal to its children nodes. So the minimum value is always at the root. For an example, we can take so this is an example for a min heap. So those are the two properties a heap must satisfy. Now let's look at the word heapify. So heapify is the process of adjusting a tree, a binary tree or a subtree in a binary tree so that it satisfies the heap property, max heap property or the min heap property. Heapify is the cooperation used in both building a heap and restoring a heap after removals. There are two main methods to fix a heap after it is destroyed. First one is the Up-Heap, also called as the bubble up or the sift up. The other one is the Down-Heap. It is also called as the bubble down or sift down. Now let's look at these methods one by one. Now let's look at Up-Heap, which is also called as bubble up or sift up. This is used when a new element is inserted at the end of a heap array. So this newly inserted element can be greater than its parent. So this Up-Heap moves it up until the parent is greater than or equal, and it restores the heap back. So now let's look at the Java code implementation for Up-Heap. So we have a reusable helper here called Up-Heap, and it works on any integer array heap and a position index. There is a variable declared child pointing to where the new element lives. Then int parent equals child minus 1 divided by 2 computes the index of its parent in the 0-based binary heap layout. Next we enter a loop. So in this loop it keeps running as long as we have not reached the root. So it can be checked by child greater than 0. And our new element is larger than its parent, and this can be checked by heap child greater than heap parent. Inside that loop we do the classic 3-step swap. In the swap we temporarily hold the child's value in TMP so we don't lose it. Then we overwrite heap child with the parent's value. So the larger parent floats down, and finally we put the original child value, which is stored in TMP now, into heap parent. So now we recompute. So now we update our pointers with child equals parent and recompute parent equals child minus 1 divided by 2, so we can test and swap again until the heap is properly restored. Now let's follow up with an example. So this is the initial state of our heap array, and this is the tree view. There are 5 elements. Now we want to insert 45 to this heap array. So we are inserting it at the end, and now our I is equal to 5. Then we want to find the parent, index of the parent of that newly inserted element. So as we discussed in the code, this is how we find the index of the parent. Now here the index of the parent is 2. That means the value is 40. So now we are comparing parent with the child. Now the value of index 2 is 40, and the element at index 5 is 45. So when we compare it, the parent is less than its child. So we have to swap them. After swapping, this is how our array looks like. We swap 40 with 45, and now our I is equal to 2. This is the tree view of our array now. Now since our I is equal to 2, again we have to find the parent of I. To that we are using this formula, and we find the parent of our I. Here parent of I is at 0th index. So at 0th index, that means our root is 50. Value is 50. Now we compare 50 with 45. 45 because value of I is 45. So since 50 is greater than 45, there is no swapping. So our final array looks like this. And our tree view, the final tree view is like this. So this is an example where we used Up-Heap for a max heap. Now let's look at the Down-Heap method. So Down-Heap means that when we remove the root and after removing the root, we move the last element into index 0. And then we restore the heap by moving that value down until its children are no larger. Now let's look at the Java code implementation for Down-Heap. So we have a reusable helper method called Down-Heap, and it works on an integer array A starting from the index I and continues as long as we are within the heap size, and it is specified by heap size. Inside we enter a while loop that runs as long as the left child of the current node exists, which is checked using the condition left I less than heap size. Since if there is no left child, the node must be a leaf and we can stop. Then we assume that the left child is the larger one by writing int larger child equals left I. But we immediately check if a right child also exists and happens to be greater than the left child using the condition if right I less than heap size and a right I greater than a left I. And if that's true, we update larger child equals right I to point to the right child instead. Next, we compare the current parent node at index I with its larger child using if ai less than a larger child. And if the parent is smaller, we call the helper method swap ai larger child to exchange their values, so the larger one moves up and the smaller one moves down, maintaining the max heap property. After the swap, we set I equals larger child to continue down the tree and repeat the process with the new subtree. But if the current node is already greater than or equal to its largest child, we break the loop with break. Since the heap property is now satisfied and no further action is needed, finally the helper methods left int I and right int I return the index of the left and right children of a node at index I in a zero-based heap using the formulas 2 into I plus 1 and 2 into I plus 2. And the swap method simply swaps two values in the array using a temporary variable to safely hold one of the values during the exchange. So this is how we can implement a Down-Heap in Java. Now let's look at an example of Down-Heap. This is the initial state and our heap size is 6 right now, and this is the tree view of our initial state of the heap array. Now we are extracting 50, which is the root, and replacing it with the last element, and then we remove the last element. So after all that, this is what our array looks like. Now our heap size is 5 and we are starting I at 0 and we are assuming that it is the largest element right now, as we discussed earlier in the code. So now you can see the last element has come at index 0, And now we are comparing it with its children. As we discussed in the code, we are taking the left child and the right child like this. 2 into I plus 1 and 2 into I plus 2. 2 into I plus 1 gets us the left child index, and 2 into I plus 2 gets us the right child index. So right now our value of the element at index 1 is 30 and 2 is 45. Index 1 and 2 are the children of I now, 0th index. So 30, our left child, is less than 40, so no swapping. And our right child, 45, is greater than 40, so a swapping happens. So we are swapping 45 with 40, like here. 45, we are swapping these two, and after swapping it looks like this. Now our I is equals to 2. So this is the tree view of the final result. So this is what is called as the down heap. Now let's implement a max heap using an array in Java. So here we have our static method that takes an unsorted integer array and transforms it into a proper max heap, returning the updated array. Inside, int n equals array.length stores the total number of elements in the array in the variable n. Then we enter a for loop that starts from the last non-leaf node using int I equals n divided by 2 minus 1, because in a complete binary tree, all nodes from index n divided by 2 onwards are leaves and don't need to be heapified. We then move from that node backwards toward the root using I greater than or equals 0. And at each step we call our down-heap method, which we have discussed earlier, to push the element at the current node down to its correct position if it violates the max heap property. This ensures that every subtree becomes a valid max heap, and by the time we reach the root, the entire array satisfies the max heap structure. Finally, we return the modified array using return array. This is how we can build a max heap using an array. Okay, now let's look at the applications of heaps. One of the applications of heaps is priority queues, and another one is heap sort. So first, let's look at the priority queues. So as we already know, priority queues serves the element with the highest or the lowest priority first. So in heaps, if we take a max heap, it serves the element with the highest value as the highest priority element, and in a min heap it takes the lowest element with the lowest value as the highest priority element. So if we take some operations of priority queues using heap, we can take insert. Insert x. This means adding an element to the heap. Also we can say so get min or get max return the highest or the lowest priority element. Also there are operations remove min, remove max. So these operations just removes the root. So what we talked about was one of the applications of heaps, which is the priority queues used in heaps. Next, let's look at the heap sort. So a heap sort is a comparison based sorting algorithm, and it uses a heap to efficiently sort the elements. So there are some steps to perform this heap sort. First, we need to turn the array into a max heap or a min heap, depending on whether we want to sort the array in ascending order or descending order. Then we have to repeatedly swap the minimum or the maximum element, which is at the root, with the last element, and we reduce the heap size. Then we have to heapify under this new root. So we have to repeat this process until the array is sorted. So this is what we have to do in order to perform the heap sort. Now let's implement this heap sort in Java. So we have a method that sorts an integer array in place using the heap sort algorithm. Inside, we first get the number of elements using int n equals array.length and store it in n. Then we begin step 1, which is building a max heap from the input array by calling our previously implemented method build max heap. So all parent nodes are greater than or equal to their children, making the largest value sit at the root, where index 0. After that, we move on to step 2, where we repeatedly pull out the maximum value from the heap and move it to its final sorted position at the end of the array. This happens in the for loop, which starts with int n equals n minus 1 and runs backward until the array is sorted. Inside the loop, we perform a swap. We store the root value, which is the largest value, into a temporary variable tmp, then move it to the end with array end equals tmp and bring the last unsorted element up to the root position with array 0 equals array end. Temporarily break in the heap property. To fix that, we call our previously created method Down-Heap, which is where we implemented it when we discussed the Down-Heap. So it restores the heap property from the root down to ensure the remaining unsorted part of the array is still a valid max heap. We repeat this process until the entire array is sorted in ascending order. So this is how we can implement a heap sort. Since we look at the code implementation of the heap sort, now let's look at an example. So suppose we want to sort this array in ascending order. Since we are sorting in ascending order, we need to build a max heap. So we have to convert this array into a max heap started from the last non-leaf node. To find the last non-leaf node, we are using this formula. N equals 5 here. So our last non-leaf node is 1. After getting it from this formula, n divided by 2 minus 1. So we are now heapifying at I equals 1. So the element at 1 is 10 and the children are value of children are 5 and 1. So since they are all less than the parent, there are no changes happening. Now we are moving to 0. So now we are heapifying at I equals 0. Now the value of the value at 0, index 0 is 4 and children are 10 and 3. So since 10 is greater than its parent, we are swapping 4 and 10. 4 and 10. So now our array looks like this. And the tree view is this. Now we are heapifying 4 at index 1 now. So the value at index 1 is 4. Children are value at 3 and value at 4. Element at 3 and element at 4. 5 and 1. So since 5 is greater than its parent, which is 4, we are swapping. So after swapping, this is the tree view and this is the array view. 10, 5, 3, 4, 1. Now our array is in the max heap form. We have converted this array into a max heap now. Now we have to do the heap sort process. So in the heap sort process, we have to repeatedly swap the maximum or the minimum element, which is the root, with the last element. In this case, we are swapping the maximum element and we reduce the heap size. And then we heapify down the new root and we repeatedly do this until our array is sorted. So here in the iteration 1, we are first swapping the root with the last element. So 10 is swapped with 1. So now since this is a max heap, our largest element is at root. So by removing the root and moving it to the last, we are placing it at its final position because we are arranging this in the ascending order. So 10 is in its final position here. Now we are heapifying under our new root. So our new root is at index 0 and we are heapifying down. Now our heap size is 4. So we compare 1 with 5. It's children nodes. So since 5 is greater than 1, we swap. And this is our tree now. And we then compare 1 with 4. And since 4 is greater than 1, swap. We are swapping 1 and 4 here. Now after swapping, this is what happens. So in the iteration 2, we are swapping the root with the last element. So right now, our last element is 1. So we swap 5 with 1. So in the iteration 2, after swapping 5 and 1, this is what our array looks like. 1, 4, 3, 5, 10. Now 5 and 10 are at the end of the array. So they are already sorted now. Now we are heapifying down our new root. So our heap size is now 3. So now we are comparing 1 with 4. 1 with 4. So since 4 is greater than 1, we are swapping. We are swapping these two. So now in the iteration 3, again we are swapping the root with our last element. Now our last element is 3. So we are swapping 3 with 4. So in the iteration 3, after swapping This is what it looks like. So now we are heapifying under index, heapifying down, index 0, and now our heap size is 2. Now we have to compare 3 and 1. Since 3 is greater than 1, there are no changes. So this is what our final array looks like in the tree view. So in the tree view at iteration 3. So when it comes to iteration 4, we swap 3 and 1. So after we swap 3 and 1, this is what our final result looks like. So our final array is arranged in the ascending order now. So this is how the heap sort works. Now let's implement some heap operations using Java. First, let's implement insertion operation. So inside our max heap class, we have declared a private integer array heap to store the elements, and a private integer size to keep track of how many elements are currently in the heap. Next, in the constructor public max heap int capacity, we initialize the heap array to the given size using heap equals new int capacity and set size to 0, meaning the heap is currently empty. Then we define the insert method which is responsible for adding a new value into the heap while maintaining the heap property. The first thing we do inside this method is check if the heap is already full by comparing size equals heap.length. And if it is, we throw an exception to prevent inserting beyond capacity. Otherwise, we assign the new value to the end of the current heap using heap size equals value, placing it at the next available position. Then we call a helper method. Then we call a Up-Heap method to heapify. We have implemented it before, and we can call that function here as well. So I have called that function here, and it shifts the value upward into its proper position by comparing it to its parents and swapping as needed to maintain the max heap structure. After this, we increase the size counter with size ++, since we have successfully added one more element into the heap. So this is how we can implement the insertion operation using Java. So now let's implement the deletion operation in Java. So in this code, we have the constructor to initialize the heap with the given capacity and the method to insert a new value into the heap, just as we discussed earlier in the insertion operation. And next, we start with the method remove root, which is a method that removes and returns the root element of the max heap. This root is always the largest value in the heap. Inside the method, we first check whether the heap is empty using if size equals 0. And if it is, we throw an exception. Next, we store the root value located at index 0 into a variable named max using int max equals heap 0, because this is the value we will eventually return. Then we move the last element in the heap up to the root position using heap 0 equals heap size -1, which temporarily breaks the heap property but allows us to avoid a gap in the array. After that, we reduce the size of the heap with size minus minus. Since we have logically removed one element from it, to fix the heap after the replacement, we call down-heap method, as we discussed in the down-heap, which shifts the new root to its correct position, restoring the max heap property. Finally, we return the original root value that we stored in max using return max, completing the removal operation. Since we are at the end of this video, let's summarize what we have learned. So first we discussed about what a heap tree is, and then we discussed about the properties which are satisfied by heap trees. First one is the shape property. Under that, we discussed about the complete binary tree structure, and the other property is heap property. Under that, we discussed about the max heap and the min heap. Then we talked about the heapify. Under that, we talked about the up-heap and the down-heap. Then we talked about the applications of heaps. So there we talked about priority queues and heap sort. Further, we talked about some operations in heaps like insertion and deletion, and we implemented them in Java. Also, we implemented a max heap using an array in Java. So this is all. This is what we learned in this video. So I hope you guys have learned something out of this video on heaps. So thank you very much for watching my video, and stay tuned for more videos like this.